In the previous section, we described troubleshooting single cycle time loop errors. By the end of this module, you will be able to use pipelining to increase the throughput or speed of an FPGA loop. In this section, we'll talk about a technique called pipelining. And this is a technique that you can use to increase the throughput or the speed of an FPGA loop. So what pipelining will do is it takes advantage of parallel processing capabilities of an FPGA, and by taking advantage of this, we're going to increase the efficiency of our code. Okay? So the first thing you need to do for pipelining is you'll need to divide your code into discrete steps. So let's take a look at our block diagram here on the left. So let's say we've got some code, and we were able to divide that code up into section A and section B. Okay? So for this example, let's just say section A takes 5 milliseconds to execute, and section B also takes 5 milliseconds to execute. Okay? If we look at that example on the left, the total amount of time it's going to take to execute A and B is going to be 10 milliseconds, right? Because they're 5 milliseconds each. One way we can try to optimize this a little bit more and decrease the loop period is we can do pipelining. So if we take a look at the block diagram on the right, that's exactly what we've done. So in this case, we pipelined this. We've separated sections A and section B, and they're now happening in parallel. So on the left, they're happening sequentially, but on the right-hand side, they're happening in parallel, so we can try to optimize it for speed, right? If we take a look at the diagram on the right, we'll have section A. It's going to send an output to the shift register on that first iteration, okay? Now, on the second iteration, what A had sent to the shift register is going to come out of the shift register on the left and feed it into section B, and B will be able to process that code. But at the same time, in parallel, A is already processing the next piece of data. So at this point, if we take a look at the period of this loop, because section A takes 5 milliseconds to execute and section B takes 5 milliseconds to execute, if they're happening in parallel, this entire while loop is actually executing every 5 milliseconds, which is twice as fast as what we had before. And this idea is what describes pipelining. Okay, so we're using pipelining now to increase the throughput and speed of this loop. So in this slide, we're doing the same thing we did on the previous slide, except we're using a feedback node instead. Okay, so a feedback node has the same functionality as a shift register, but just because of the way that it looks, it's able to maintain a more congruous VI appearance. So if we take a look at the code on the left, that's our original sequential code. We can kind of keep that same look and feel, but add the pipelining by inserting a feedback node in between. Okay, so a feedback node, the functionality is the same as a shift register. So on the very first iteration here, we're going to have section A send some data to the feedback node, and then the next iteration of this while loop, the feedback node is going to output the previous value that A had put into it and send it to B. And then at the same time, A is going to be executing in parallel. So it's the exact same behavior that we saw in that previous slide with the shift registers. We just have a different appearance and a different way of showing it by using a feedback node. So let's take a look at a basic example of pipelining inside LabVIEW. So here we've just got some simple code, and if we take a look at it and we kind of count up what's going on, it's going to take 5 cycles for the code to execute and 2 cycles for the loop to execute. Okay, so let's say that input control equals 1 for iteration 0, 1, 2, and 3. Well, the output is going to be 1, 5, 9, and 13. And we have all of those functions happening in sequence. Okay, so let's think about how we could pipeline this and make it a little bit more efficient and increase our rates and throughput. So here we've pipelined the code on the right-hand side, and we've done that by using shift registers. So what's happening here is kind of what we described earlier. If we take a look at the code on the right-hand side, it's going to have a faster loop rate, and that's because we pipelined it. So the very first iteration, we're going to get our input of 1, we're going to do the multiply, and we're going to send it into our shift register. Okay, the next iteration of the loop, that data is going to come out of that top shift register, and it's going to go inside the scale by power of 2 function and send that result into the next shift register. On the third iteration, that original data from our input is going to propagate down to the bottom shift register, and then that data is going to come out, and then we're going to get our first valid output. Okay, But at the same time, the increment function, the scale by power of 2, and the multiply function are all happening in parallel at the same time. So we're able to decrease the loop period for this loop, which is going to allow us to have faster speeds and more throughput. So if we take a look at that this particular example, it used to take more than 5 clock cycles to execute in our previous example. And by pipelining it, we've been able to make the code inside on the right-hand side only take 3 cycles to execute for the code and an additional 2 for the while loop overhead. Okay, so we've decreased the time that this while loop needs to execute. So if we look at that third bullet now, let's say we have an input of 1 for iterations 0, 1, 2, and 3. Well, if you look at the output, the first 2 outputs are not going to be valid data because the original data has not propagated down to that bottom shift register yet. So you're going to have to wait until the third iteration of this while loop for that first valid output, which is 1 and then 5. So here we take a look at that same example of pipelining that we did in the previous slide. And instead of using shift registers, which kind of makes the code kind of broken up and a little bit hard to read, instead we're going to replace those shift registers with feedback nodes. And this is going to be the exact same functionality, but if you take a look at the code on the right, it's a little bit easier to read and it's easier to kind of see the sequence of the calculations and algorithm here. Okay, so a lot of times you'd want to use feedback nodes instead of shift registers just to make your code a little bit more readable. So here we see another example of pipelining. So let's take a look at the code on the left. So the code on the left is going to be our code that is not pipelined yet. Okay, so if we take a look at what's actually happening, everything is happening sequentially. So first you have the analog input with that FPGA I/O node, and that analog input is going to take a long time. It's going to take 170 ticks. Then you have some other calculations like scaling, and that's going to take another 2 ticks. And then you have your analog output, which is going to take 38 ticks. And then you've got your overhead of your while loop of 2 ticks. So if you take a look at that, that's going to be 212 clock cycles, which is going to be about 5.3 microseconds. Okay. So now let's take a look at the example on the right where we've actually done some pipelining. Okay. So by looking at the code on the left, we saw that the analog input took a long time, and we could do pretty much the rest of the code at the same time as the analog input. So what we've decided to do is we pipelined it. So you can think of section A of your code of the pipeline is going to be your analog input. And then section B that gets pipelined is everything else. Okay? So notice that we've got our feedback node separating our 2 sections. So we've got a feedback node separating the analog input and the analog output and the scaling functions. So if you take a look at the graphic on the bottom right, we see that our analog input is going to take 170 ticks, but the same time in parallel, we're also doing the scaling and the analog output, which is a total of 40 ticks. So if we take a look at that, we take the longest path, which is the 170 ticks, plus the while loop overhead of 2 ticks, and we've got a total clock cycle of 172, which corresponds to 4.3 microseconds. So by doing pipelining in this case, we made our while loop execute 19% faster. Okay, so let's walk through an example optimization. So what do you do if your diagram executes too slowly? So if we take a look at this example, we see that our code takes 12 cycles to execute. So what's the first thing we can do? Well, we can take a look at our code and we can just try to look at some best practices and replace some of the functions to have the same functionality, but use more efficient coding. So let's take a look at the next slide for what we can do. So here we see that we've shortened the longest path by using some basic optimizations. So we've gone from 12 cycles down to 9 cycles. Okay, so what else can we do? On this slide, we've shortened the longest path even further by implementing pipelining. So notice that we've pipelined this, and as a result, we are down to 6 cycles. Okay, so this is just an example of how to do some optimization. First, do some basic optimizations, and then if you need it to be even faster, then you can implement some pipelining. Now you can use pipelining to increase the throughput or speed of an FPGA loop. Next, we will use pipelining to increase the throughput or speed of a single cycle time loop.